Tomorrow I'm not going to be able to hold my office hour at 10:30 to 12:30, which is what is supposed to be listed in the syllabus. It'll be from 2 to 4 p.m. in the afternoon. So in case you want to see me for discussing your solution to the first problem set, you are free to do so. Some of the people are missing, and I closed the door, so they will be discouraged to come in. So let me just open the door just for those who might have not arrived yet. Okay, our chairman did not assign a course assistant to this course because there are not enough teaching assistants in the department. For that reason, I decided not to grade your homework, so I'm just assigning the problem sets. Nevertheless, I talked to my old teaching assistant, my PhD student, Hatice, and she agreed to solve the problems on the board on Wednesdays in the second hour from, from 3:40 to 4:30. So in case you solve the problems prior to coming to class on that day, you may actually, come with a well-prepared mind, more active, and when she solves the problems, you'll better receive the solution. If you don't attempt the solution beforehand, you may, of course, passively realize what the solution is all about. Nevertheless, it doesn't really work as good as well as when you would prepare a priori. Is everybody? Well, we'll just keep the door. All right, you guys come in a little bit earlier. Try to come in at least a little bit earlier, okay? Here's a bus scheduling problem. Some of you might have seen these examples in your undergraduate introductory linear programming course because they are simple-minded and they are good to present for undergraduates. For you, these are probably simpler, but not all of you come with the same background. So I'm giving you some of the more simple problems right now, and then we'll go into a little bit more general problems in a few minutes. Okay, so in this problem, we've got, well, we're trying to plan the number of buses that we want to operate in a fleet when the buses work in 6 different periods. Now, the first period refers to the time slot between 12 to 4 a.m. The second one from 4 a.m. to 8 a.m. The next one from 8 a.m. to 12 noon. This one is, of course, midnight. Okay. And so on and so forth. 12 noon to 4 p.m. and then 4 p.m. to 8 p.m. and then 8 p.m. to 12 midnight. Okay. We've got demands for the buses. These are average number of buses you need. We've got 4, 8, 10, 7, 12, and 4 in these periods. Each bus operates for 8 consecutive hours. Of course, you schedule the bus at the beginning of a period, and then it just goes on for 8 hours. Find the minimum number of buses to operate this system on a daily basis. Okay, so in this problem, you may come up with different decision variables, but the one that comes in most handy happens to be the following one. Rather than associating your decision variables with the number of buses used in a given period, which is typically what many people tend to do, we use an alternative, which is the following. You want to define xj to be the number of buses that starts operation at the beginning of the jth period, which is different from what you might have come up with at the beginning. Okay, so xj is the number of buses that begin service at the beginning of period j. That's the way I define it. With that, things will be quite easy. All we have to do is we want to minimize this sum subject to meeting the demand in each of the periods. The first period has a demand of 4 buses, so you want 4 buses in operation, 4 or more buses in operation in that period. Now, the buses that will be in operation in period 1 will be either those that begin their operation at the beginning of period 1, or those, this is an ongoing operation, those that began at what time?
6.
In period 6, right, from the day before. So x1 plus x6 will account for the number of buses in operation in period 1. Similarly, the buses that will be in operation in period 2 will be those that either started 1 period earlier or at that period, and this should be greater or equal 8. You got the idea, right? And then the next one will be x2 plus x3. This is for period 3. Those that started just 1 period earlier, plus those that started in this period. That should be greater or equal 10. x3 plus x4 greater or equal 7. x4 plus x5 greater or equal 12. And finally, x5 plus x6 greater or equal to 4. Plus, each xj is non-negative, and of course, each xj is integer. You don't have fractional buses. If you ignore the integrality requirement, this is a linear program, if you ignore that. If you don't ignore that, it's an integer programming problem. Fine, you'll know how to solve these problems also. How many people have seen this before in at least my course? Okay. Well, let me give you a little bit different one. This is similar. So at least with these problems, sometimes there's a certain pattern. If you master the pattern, you're done. This is quite similar. Another example. Weekly night shifts for nurses in a hospital. Okay? So this time, instead of buses, you've got nurses in a hospital. The night shift goes from 12 midnight to 8 a.m., 8 hours. Okay? And we assume, again, we have a certain demand for the night shift on different days of the week. DJ is the demand for nurses. And the night shift in day J. J goes from 1 to 7. We've got 7 days in the week. We assume these are known numbers. In other words, as in the previous example, just assume there are certain numerical values here. Each nurse works for 5 days in a row, okay? In the night shift. So again, I'm going to define xj to be the number of nurses who will begin their work week on day j. Similar to that. The only reason I'm giving this, in formulating problems in the real world, you should try to capture certain patterns or certain structural elements which are common in the literature on linear and linear integer programming. So if you capture that, you'll probably be in better shape than attempting to sometimes formulating problems in quite unaccustomed ways. Be innovative, but sometimes, I remember such cases. Actually, there was one reported by, well, I'm not going to give the name right now, but someone, a colleague of mine in the United States, there was a certain problem. She gave the problem to her PhD student, and the PhD student came up with a formulation with lots of zeros and ones, 0, 1 variables, and so forth. And then it turned out that once you try to solve that problem in that formulation, after operating the solver, say simplex, for 3 days, 72 hours, you're not able to really get the solution. This is a linear integer programming problem with many integer variables. And then, of course, my colleague, the supervisor of the PhD student, she said this is not going anywhere. So she decided to sit down and study the problem on her own. And then she came up with the so-called embedded network flow structured problems. Now, network flow structured problems are easy to solve. And if they are more intricate than a simple network flow structure, if they are embedded into one another, yes, it's a little bit more difficult. But normally, you should be able to solve it in a much faster way than a typical, naive formulation. So, her formulation was able to generate the optimal solution in a matter of seconds, 30 seconds or so, whereas the other formulation was not able to generate a good enough solution within 72 hours. This is the difference. So keep that in mind when you work on, well, this course is not really on formulating problems, but nevertheless, when you work on your master's or PhD thesis, you should keep that in mind. A good formulation always works much better. All right, so what's the formulation here? We want to minimize x1 plus up to x7, subject to the first day, D1. I need those nurses that start on day 1 plus those that started back on day 7, 6, we go back. Okay, how many? X5. How many more? X4. How about X3? 1, 2, 3, 4, 5. So, since a nurse works 5 days in a row, this is how far back I go. For the second day, similar. X1 plus X2 plus 5, 6, and 7, etc. The last one will be D7. And what is the situation for that? X7 plus X6 plus X5 plus X4 plus X3, right? That should be the situation. All right, again, Xj are non-negative and Xj are integer. Okay, same structure for both problems. Let me give you a financial planning problem, which some of you might have seen again earlier in undergraduate courses. You've got money-making activities A and B. These are available at the beginning of next 5 years. If you invest $1 in A, at the beginning of year 1, returns $1.40. Two years later. And whatever you get, you can reinvest it again in the future. Okay? This is for A. And for B, we have the following situation. $1 invested in B at the beginning of year 1. Returns $1.70 3 years later. You can also reinvest this, but we're going to use a planning horizon of 5 years, so there's no point in doing that. Okay? You want to maximize your total return at the end of the 5th year. So reinvesting will not do the job. Okay? Okay. And money-making activities C and D also become available later. $1 invested in C at the beginning of year 2 returns 190. Returns $190 at the end of year 5. And $1 invested in D at the beginning of year 5 returns 1.30 at the end of year 5. Okay, so this information is given. You begin with $50,000 in your hand at time 0, or the beginning of year 1, and you want to maximize the total money in your possession out of this investment strategy at the end of year 5. So maximize the total return at the end of year 5. That's what you want to do. How many people have seen this before? Okay, at least the minority has seen it. Many of you had not seen it. Okay, so in this case, you might want to define a number of decision variables. For example, I may call XIA the amount of money invested in money-making activity A at the beginning of year I. Okay? The amount invested in A at the beginning of year I. Of course, you define the variable only for relevant combinations of I and A. Similar definitions for XIB, XIC, XID for appropriate combinations of indices I and activity indices. Okay? Let me also define SI to be the amount of money not invested at the beginning of year I. The amount which is available but not invested. So this is the money you keep in your pocket rather than invest it. Okay, I've got too little space left here, so let me just continue on this side. What is my total return at the end of the 5th year? According to the information we've got here. Well, money-making activity A returns some money at the end of 2 years. So to get something from A, I must have made some investment at the beginning of year 4. 4 and 5 gives you 2 years. So I'm going to have X4A, which is the money I invested at the beginning of year 4 in A, and the return for that is going to be 1.4. Does that make sense? All right, so that's the portion coming from money-making activity A. What about money-making activity B? It gives you 1.7. And that money will come from where? X3A. 3B, sorry. X3B. Whatever you invest at the beginning of year 3 in B will return 1.7 times as much at the end of year 5. What else? C and D. $1 invested in C at the beginning of year 2 returns 1.90 at the end of year 5. So there's only one here, X2C, and that's going to be 1.9. Okay. Plus, the last one is this one. $1 at the beginning of year 5 returns 1.3. So 1.3 times X5D. That's the money you will have in your pocket at the end of year 5. Subject. Now my first year investment.
Plus S6.
No, there's nothing else. There's nothing else. There's nothing else. This is all you've got at the end of the 5th year. 1, 2, 3, 4, 5. So anyway, if you look at it, well, what did you say again? Maybe? X6? Oh, S6. S5. Oh, I see. I see. I thought you said something else. Okay. So if you did not, if there was a leftover money at the beginning of year 5, which you kept to yourself without investing, it will be available at the end of the year with no additional return. So I agree with you. Okay, good. All right, what is the condition for the first year investment? Well, I've got $50,000 at the beginning of year 1. And that may go into, that will be split among 3 alternatives. One is X1A. The other is X1B. And the last part is, if you decide not to invest some money, S1, that's the leftover. This should add up to 50,000. What about the second year? Do I have anything coming from it? Well, I don't have anything coming from any of the previous investments on the second year. What is the money I have available in the second year? S1 is the only money I have available, which is a variable, but let's just put it on the right side. What are my investment options here? X2A, X2B. Is C available here? No, it's not available yet. Plus S2. If I keep something in my possession, that will be S1. Because at the beginning of S1, I've got only S1 dollars available.
Sure. Question.
C is
Why is not C available? Because it says it's at the beginning of the year 2.
Oh, sorry, it's available. Yeah, it is available. So let's put that in also. X2C, right? Yeah, it is available. All right, this is for the first year. Year 2, year 3. You tell me. X3A, X3B, X2, X3C. No?
No, only S3.
Only S3 is equal to what you've got at the beginning, or maybe something else. Hmm? You've got the returns, right?
Yeah.
How much?
1.4 x1a.
1.4 x1a. This is money that's coming back, plus anything else? That's it. That's it. Okay. So on the right side, we've got the total money available at the beginning of that particular year. Okay? Next, year 4. X, I don't know if I would make any investment in A. Yes, since it's here, I better include that. But I wouldn't make any investment in B because it's, it won't return anything within the planning horizon. What about C? C is not available, and D is not available. So we've got S4 here. And that's going to be equal to S3 plus 1.4 X2A plus 1.7 X1B. Anything else? No, nothing else. Finally, year 5. Beginning of year 5. The objective function is the end of year 5, so this is the beginning of year 5. Any investment? In A? No. In B? No. In D? Yeah. The only investment you can make is X5D. Plus, typically you won't have any money left in your pocket. Nevertheless, let's just put that in. And what you've got here is S4 plus 1.4 X3A plus 1.7 X2B. Anything else? That's it. Plus all variables X. $1 invested in D at the beginning of year 5 returns 1.30. What about that? It's in the objective function. I don't have anything else here. This is the money invested in D at the beginning of that year. That's it. All right, so we've got xi j greater or equals 0 for all relevant combinations of I and j, I going from 1 to 5, j going A, B, C, D. Okay? That's it. And S, Si, also non-negative. All right, simple enough. Sometimes they are not very simple, but nevertheless, this is pretty much straightforward. How many people have bought the book by Bazara, Jarvis, and Sherali? All right, you should get it. How many people bought the book by Bertsimas and I can't say his name. Csikszentmihalyi. Yes. How many people bought that book? Huh? You should get that also. It's good to have those two books in your library, believe me. Not just for the course, but for your future professional activities. All right, especially for those of you who are planning to do some PhD work, it's good for you to have those books. Okay. How many people have looked at the problems I assigned? Did you do anything with them?
Yeah, first two questions.
You did the first two questions. What about you?
Well, actually, I did a couple of them, but I guess the version of my book is the older one. So I'm not sure if the numbers are the same.
Actually, you made a point here. I've been using the second edition of the book, whereas maybe your edition is the fourth edition, or maybe is there a fifth edition? I don't know. So anyway, use the second edition. You know, or maybe I'll give you out. This is just too much extra work for me. Nevertheless, I'll try to see if the numbers match with the new one. Okay? Another problem in the remaining 5 minutes or so. Maybe I should just get the fourth edition and see how the problems are. Suppose you have a chemical process where you produce chemicals ABC with inputs X and Y. These are capital X and capital Y. Later on, if I start using small lowercase x and y, don't confuse the variables with the actual inputs. Okay. Now we've got some information. Produce 1 ton of A, you need to input 1/4 ton X. Okay. Similarly, 1/4 here, 1/12 for this one, 1/2 here, 1/10, 1/12. Okay, there's a least amount of production you should have, and those are given as 4 tons for A, 2 tons for B, and 1 ton for chemical C. There's a purchase cost, $250 per ton of input X and $400 per ton of input Y. There are also processing costs. Which amount to $250 and $200. Excess production of a chemical has no value, and you're asked to find the input mix that minimizes the cost. While, of course, meeting the least production quantities, the demands. These are also per ton, so you might want to add that. Okay. Processing costs. Okay. This problem is really quite simple. How many people have seen this? How come? Because you were all in the same class, huh? You just saw it? You don't remember it, okay. All right, so in this problem, we may define two decision variables, x and y, small x and y. X is the tons of input x to use. And the other one is tons of input y to use to get the chemicals. All right, what do I maximize or minimize here? Well, we're minimizing the cost. So what is the cost that I'm supposed to minimize here? $500. 500 times x plus 600 y. Since each cost is given in terms of per ton, so this is simple, straightforward. Subject to, you need to produce at least 4 tons of chemical A, 2 tons of chemical B, and 1 ton of chemical C. So to produce 4 tons of A, what do you need? 1/4 and 1/2. Okay. Similarly, 1/4 and 1/10. And 1/12 and 1/12. Simple stuff. Okay? Okay, let's take a 10-minute break, and then we continue with a little bit higher level examples. Okay?